Hi everyone, my name is Dennis and I'm going to talk about our paper ToothPicker Apple Picking in the iOS Bluetooth Stack. In our paper, we analyzed the remote attack surface of the iOS Bluetooth Stack with a special focus on protocols that are available prior to pairing. For this, we implement an in-process fuzzer based on Frida that we call ToothPicker. So let's look at Bluetooth in the Apple ecosystem and why this is an interesting target. In general, the Apple ecosystem really encourages users to turn on Bluetooth, so there's functionality like handoff and continuity, which really relies on Bluetooth to be turned on to function properly. And on the other hand, there are devices like the Apple Watch or the AirPods and other Bluetooth headphones in general, as Apple removed their headphone jack. What we found out during our research is that Apple actually implements 3 different Bluetooth stacks. So there's a separate implementation for macOS, another implementation for iOS, and a third implementation for RTKit, which is Apple's real-time operating system for AirPods, the Siri remote, and other Bluetooth peripherals. So the reason why we chose iOS as our target is that firstly, for macOS, there has already been some work in the past, which already revealed a few vulnerabilities in the Bluetooth stack. And on the other hand, because of the bad inspectability of RTKit devices and especially the AirPods. So there's no public or official way to debug them. And it's really hard to not possible at all to obtain logs. So in general, iOS is a pretty attractive target. It implements most of Apple's proprietary Bluetooth protocols and protocol extensions. And also, due to its nature, iOS devices and especially iPhones are carried around by people all the time and everywhere. So while Bluetooth is not the classical remote zero-click attack surface for targeted attacks against individuals, Bluetooth RCEs are easily warmable. So if there's one infected device, it's very easy to spread around. And given the large number of iOS devices, this seems like a reasonable attack. As I've mentioned before, Apple actually implements quite a few proprietary Bluetooth protocols and extensions. And here's a short list of some of the protocols that we found during our research. If you're interested in one of these protocols, I would like to refer you to our paper where we try to describe what the purpose of some of these protocols are. Now, given the interesting attack surface and all of the proprietary stuff that Apple implemented, we wanted to sort of develop a fuzzer where we could evaluate the quality of the implementation of all these protocols. However, it turned out to be not so easy to fuzz Bluetooth on iOS. And this is mainly due to the general complexity of Bluetooth, but also due to the complexity of the main component for Bluetooth on iOS, the Bluetooth daemon Bluetooth D. So, Bluetooth D is a rather complex piece of software. So firstly, there's lots of interaction with other system daemons. So for example, sharing D, Bluetooth audio D, Wi-Fi D, and quite a few others. And also there's a constant interaction with the Bluetooth chip. So the Bluetooth daemon always, has to communicate to the Bluetooth chip all the time. Bluetooth D also runs in multiple threads. So firstly, there's the most important thread, the stack loop, which is exactly the loop that is responsible for the communication between Bluetooth D and the Bluetooth chip. And then there's also the RX loop and the TX loop for reception and transmission of data. And occasionally other threads are spawned for a lot of different tasks. So Bluetooth D is a very, very large binary file and it has almost no symbols, especially for the parts that we're interested in. So the protocol parsing and protocol reception, there are no symbols at all. This makes reverse engineering Bluetooth D quite a task. So what you can easily do now is implement an over-the-air fuzzer. So you can just take any device that is capable of generating Bluetooth traffic and then connect to your target iPhone. And over this Bluetooth connection, you can then just generate random Bluetooth data and send it over. What you can also do to the target iPhone is you can connect it to a Mac with Apple's packet logger, which helps you to inspect the incoming traffic and try to analyze what's happening. So this is pretty simple, and it has also quite a few advantages. So firstly, you have very few false positives, because anything that your over-the-air fuzzer will find as a crash, for example, an attacker will be able to do as well, because it's real physical connection. Also, it's obviously platform independent, so you can send over-the-air data to an iOS device, to a macOS device, or just really any Bluetooth-capable device. However, this approach has a lot of drawbacks. And the most important ones are basically speed and stability. So firstly, you're using a real physical wireless connection, which is always something you do not really want for fuzzing. But more importantly, there's connection termination. So in general, and especially on iOS, Bluetooth connections are very sensitive. So if an iOS device receives unexpected or invalid messages, at some point it will just terminate the connection. For a fuzzer, this is not so great, because the fuzzer would have to detect this connection termination and then would have to reconnect to the device. And this usually takes multiple seconds, which is really bad for fuzzing performance. And also things like coverage and feedback are kind of hard. So as an attacker device or as a fuzzing device, it's really hard to distinguish between connection termination and an actual crash in the Bluetooth daemon. So there are quite a few challenges, and we decided or found that we could solve a lot of them by using instrumentation and more specifically using Frida, because it also gives us a lot of other advantages basically for free. So for example, for coverage, we can just use Frida's built-in Stalker extension, which basically gives us coverage for free. It's really easy to implement. Feedback on crashes is also made very simple by using Frida, as Frida installs their own exception handler. So instead of, let's say you're generating an input that would crash Bluetooth D, in this case, the exception handler will try to catch that exception and give you more information about that instead of actually crashing. So this is great for analyzing these crashes, but also it's very great for performance, because then Bluetooth D doesn't have to restart, but you can just go on with your fuzzing. Usually if Bluetooth D would have to restart, this would also take multiple seconds, because the setup is quite large. However, the largest benefit is that we now do not rely on physical connections. What we can do is we can create virtual or basically fake connections by injecting our own code. Now that we have these virtual connections, we basically have the full control of these connections. So connection termination also isn't that much of a problem anymore. And with this, we started to implement our fuzzer ToothPicker. So this is a general overview over the architecture of ToothPicker. On the right-hand side, you can see basically the management component, which consists of input mutation using Redemsa. It stores the coverage corpus, it handles crashes, and it communicates to the Frida agent that is injected into the Bluetooth D process. And on the left-hand side, you can see that. You can see the virtual connection creation, the basic block hooking by Frida Stalker, and also at the bottom, you can see the filter of specific chip interactions, which is something I will get into later. But let's first have a quick look at the management component and at the overall fuzzing process. So in general, we're using a very simple coverage-guided fuzzing process where the computer and the manager is mutating and generating inputs and sending them to the device. So first, fuzzing input is generated. This is sent over using Frida to the injected code. The injected Frida code will execute our reception handler of the specific protocol we're fuzzing, and then we will either get back a report of the basic block coverage that we achieved, or in case a crash happened, information about that crash. The management component will then store the coverage And if the coverage is new, so if we haven't seen that coverage before, the generated input will be added to the corpus, which can then be used for mutation in further rounds. And if a crash occurs, information about that crash is stored. Now, something else we need to do is, because we are doing in-process fuzzing and we are kind of manipulating the way Bluetooth D usually works, for example, by creating these virtualized fake connections, it might happen that some of these crashes are actually false positives. So what we really need to do at the end is verify if these crashes would actually occur over a real physical connection. So what we're doing is we're reusing some of the parts we wrote for the over-the-air fuzzer, and we just send these crashes and the corresponding inputs over to our over-the-air fuzzer, and then we can verify whether the crashes we had would also reproduce on a real physical connection. Okay, so let's have a look at the more interesting part of the code that is actually injected into Bluetooth D. So please note that the following functions and structures that I'm going to show you are named by us because Apple stripped all these symbols, so we don't really know what the actual functions' names are, and we just came up with whatever would make sense in our minds. So this is the ACL reception handler. ACL is basically pretty much the lowest layer of Bluetooth protocols that can be received by a Bluetooth host. So this is basically the lowest protocol layer Bluetooth D will receive. And this is an interesting insertion point for us. So the ACL reception handler takes a connection handler as an argument, the length of the data, and a pointer to the data. Data and pointer is pretty simple. We just generate that data and we also know the length of that data. But what is not so obvious is the handle. So let's first quickly talk about what this connection handle actually is. So in Bluetooth, both the Bluetooth chip and the Bluetooth host need to know about a specific Bluetooth connection. And to reference a connection, this connection handle is used. It's comparable to a file descriptor, for example. So it's just an integer value that is used as a reference for a specific connection. Whenever a new connection is created, that connection is assigned a specific handle that is usually incremented by 1. So what we need for our virtual connection creation is exactly this handle. So what we found was that there is actually a function that we called allocate connection, which receives a Bluetooth address as argument and a state value. And this will create a Bluetooth connection structure, which is basically the internal representation of a Bluetooth connection in Bluetooth D. So now we can create internal representations. However, we still don't have that handle value that we need for our ACL reception handler. But luckily, it's actually the first short in the structure, in the connection structure. So we can just set this to an arbitrary value, in this case, hex 11. And once we did that, we can call the ACL reception handler with our crafted handle value and the length and data. So, as I said before, to forge a connection, we just call allocate connection to create a connection object. Then we set the handle value of this connection, and then we can start to fuzz. But we also need to do a few other things. Firstly, we need to filter some of the Bluetooth chip interaction between Bluetooth D and the Bluetooth chip. And this is basically due to the fact that while this connection exists in Bluetooth D, the Bluetooth chip doesn't know anything about that connection. So the connection handle value hex 11 is completely unknown to the Bluetooth chip. And usually the relationship between Bluetooth D and the Bluetooth controller is a little bit sensitive. So if one of these components receives something from each other that they don't expect or that is invalid, the component might crash or restart. So it's really important that all the traffic that is related to this crafted connection handle will not reach the Bluetooth chip, because otherwise it might get unstable or crash. However, we need to make sure that all the other traffic between Bluetooth D and the Bluetooth chip still gets through, and the communication can work as intended. What we also can do now is stabilize the connection. So for example, there is a function that force disconnects a Bluetooth connection, and we can just override that to prevent our crafted connection from being disconnected. So there are a few more details to this virtual connection creation, and there's a similar process for Bluetooth low energy connections. However, this one is a bit more complex. There is a bit more state and a few more structures that need to be created, and a few additional function calls. But if you're interested in all of the details, I would refer you to our paper and the code, so you can read about more details. So let's have a look at the results. Before we started fuzzing, we picked out a few protocols that we were seeing as a target. So this is a mix between some of Apple's proprietary Bluetooth protocols and some of the Bluetooth protocols that are in the Bluetooth standard. And we did this based on a few properties like accessibility, whether they are proprietary, and what our knowledge about this is. Once we got this list of Bluetooth protocols that we intend to target, we created an initial corpus of valid protocol messages that would occur during a real Bluetooth connection. Again, if you are interested in more of the details as to how we decided for these different protocols and how exactly we created our initial corpus, all the details, you can find them in the paper. Now, performance. In general, we're getting about 25 to 30 messages per second, which in current fuzzing standards sounds a bit slow. However, in our over-the-air fuzzer, we got about 1 to 5 messages per second, so this is already quite a big improvement. However, there are still a few bottlenecks. So the first bottleneck is instrumentation. Instrumentation in general is costly. So all the FRIDA instrumentation that is required to obtain the coverage and some of the code that we had to implement for the filtering, this just adds overhead to the fuzzing process. Also, we're using Redamsa as input mutation, and we found that this input mutation accounts for about 20% of the time it takes to fuzz one message. So there's certainly room for improvement here. And also something interesting we found is that on newer devices that have pointer authentication, the fuzzing process gets much slower. And this is probably due to the fact that our injected code and the FRIDA code needs to re-assign all the pointers that we're calling. So it's advisable to run ToothPicker on older devices that do not have pointer authentication. In total, we got about 6,000 basic blocks out of 150,000 basic blocks in total, which looks like a very small part of Bluetooth D. However, our target, the ACL-based Bluetooth protocols that are available prior to pairing, are also only a really small part of Bluetooth D. It's kind of hard to determine the exact number of basic blocks these would have. And this is due to the fact that Bluetooth D is just a really big black box. So it's not so easy to determine which basic blocks would belong to which protocol. We did a quick look at the accumulated coverage to check whether we probably covered all the protocols that we intended to do, and the coverage looked fine. But again, it's really hard to tell how much we actually covered of these protocols. So despite some of the performance issues, we found quite a few bugs and vulnerabilities. 2 of them also received CVEs by Apple in the last few months. The other ones are not fixed at all yet. However, the ones that say not fixed are really not that critical. They are mostly just crashes where none of the values are attacker controllable. So they are very, very unlikely to be critical or usable for remote code execution. So that's probably the reason why they are a very low priority for Apple right now. Something that is interesting and that was quite pleasing for us is the SMP bug here. So the SMP protocol was actually not part of our initial target of protocols. And it was discovered due to the coverage by guided mutation process. So that was quite cool to see that even though we didn't really target this protocol, that our fuzzer found something in there. So ToothPicker will be available on GitHub. And if you have any further questions, you can just contact us on Twitter or on GitHub or just via email. Thanks.